Good morning, class, and welcome to this lesson on Circuits 8, Power. Today we will be able to derive the three equations for power in a circuit and understand the kilowatt hour. So we're going to be talking about equations first, and then we're going to be talking about this concept of kilowatt hours here. So power. As we know from mechanics, power is equal to energy per time. Energy per unit of time, okay? And the unit for power is the watt. The unit for power is the watt. So nothing is going to be changed there. Power is energy per unit time, and power is known as the watt. Now, what we know about this is that power is equal to energy over time, but energy we learned in terms of electrostatics, energy is equal to volts per times charge. Okay, volts times charge. Remember that because volt is equal to electric potential energy over charge. So E is equal to VQ. So power is equal to voltage times charge over time. And as you can see from this equation, you might notice that we have charge per time. We know that current is equal to charge per time. And so we get our first equation for power. Power is equal to I times V. I times V. So we have current times voltage is equal to power. Now, that's our first equation. Okay? Our second equation is we know that V is equal to I times R. So let me erase some of the stuff over here. Okay. V is equal to I times R. So P can be equal to I times R here, because I just plugged in I times R for V. So we get P is equal to I squared R. This is our second equation for power. Okay? And our third equation for power, we can rewrite this as if V equals I times R, well, I equals V over R. I equals V over R. And so if I take this equation down here, P is equal to V over R times V. Okay, so I plugged in V over R right here for this, and then so we get power is equal to V squared over R. That is our third equation. So we have three equations. This is pretty much the main one that's typically used, but we could use this one or this one in any case. So we have P equals I times V, P equals I squared R, or P equals V squared over R. No matter what we're using here, all the units for these is going to be in the watt. So power is measured in watts, and these are three equations for power. So if we have a circuit here with a resistor, okay, and let's say we know we have a 12-volt battery and we have a 3 ohm resistor here, how much power is going to be in this circuit? I have volts and ohms, I have volts and resistance right here. So in this case, I would use P equals V squared over R because I have volts and resistance, and I would solve for this. So V being 12 squared over R, which is 3. And so this is going to be 144 divided by 3. So 144 divided by 3 is 48. So this would be a 48 watt. There'd be 48 watts of power used in this circuit. Okay, and so what equation we use is just going to be dependent upon what we're given in the actual problem. Okay, so that is the three equations for power. Let's talk about the kilowatt hour now. This is a common example because this is, at least in America, this is how we measure our energy bill. So when you get an energy bill in the mail, you're rated on how many kilowatt hours you use. So what does that mean? Kilowatt hour. Well, notice this. A kilowatt, watt, this is a unit of power, and an hour is a unit of time. Okay, so let's go back to this. Power is equal to energy per time. That means energy is equal to power times time. So the kilowatt hour is really a measure of energy. It is not a measure of power. It is a measure of energy. So when you get a bill and it tells you how many kilowatt hours you used, it's telling you how much energy you use because you're getting billed on how much energy you are using at your house. Okay, so a kilowatt hour once again is a unit of energy, not a unit of power. It's very confusing because it has the word watt in there. Okay. And so let's just do a very quick example to show this. Let's say you leave your house for a week and you want to leave a light bulb on the front porch to show that you're home. So you have a light bulb on the front porch and you have a 60-watt light bulb. Okay, so you're going to leave your house for a whole week. Okay, and you're going to turn the light bulb on and you're going to leave it on for a whole week. 60 watts. Okay, so kilowatt hour, and your bill in your neighborhood is 15 cents. 15 cents per kilowatt hour, which is a pretty standard rate. It could be less, it could be more. Okay, so um, so basically, you need to know how many watts you used. So if you use 60 watts, okay, how many hours did you use it for? Well, you used it for a whole week, 24 hours times 7 days. Okay, so 24 times 7. So we have 60 watts times 168 hours. Okay, so this is going to give us 10,080 watt hours. Because all I did was multiply 60 by 168, so I get this number right here. Now, this is watt hours, but I want to know kilowatt hours. A kilowatt is just going to be 3 units over, so we're just going to move our decimal place 1, 2, 3 over. So it's going to be 10.080 kilowatt hours. So this is how many kilowatt hours you use for a whole week for one light bulb, 60-watt light bulb. And then at 15 cents, so it's 15 cents per kilowatt hour, so I multiply this by 0.15. And this would cost me $1.51 for one light bulb for a whole week at my house. Okay, and you might think, wow, that's really cheap. That's really cheap. That's who cares about that? But that's one light bulb. If you extrapolate this out to your whole house, you might have 40 to 50 light bulbs in your house, maybe even more. And if you turn all those on at the same time and they're all 60-watt light bulbs or more, you're gonna be using a lot of energy for a whole week. Okay, which is why it's so important, or why it's so good to get the what is it, the CFL light bulbs, the swirly ones, because these light bulbs are about 11 watts approximately versus the 60 watts. So you're decreasing your energy usage down to a quarter of the usage that you did before.